It is held together by constantly rebuilding. All the time, your skin cells are rebuilding, your bones are rebuilding. You're always actually breaking down and rebuilding all the time, according to this wonderful pattern that was given to you by your parents. In the absence of this rebuilding, we have something that's called entropy. Entropy is what happens to Dennis's arm if we put it on the shelf, or that tuna fish sandwich you forgot to put in the refrigerator. It degrades. It becomes more random. It breaks down into simpler stuff. Tuna fish sandwich or Dennis's arm breaks down into something called amino acids, which are nitrogen compounds, and they begin to smell bad to us. I don't know if they really smell bad, or there's been natural selection for us to think that it smells bad so we don't get bad diseases from what we eat. I don't know. But it sure stinks. Of course, this decomposition process is essential eventually. So Dennis, someday your molecules, I promise you, will become part of other ecosystems. When you die and they stick you in the ground or they put you into cremating, and I'll beat you to it, almost certainly, if you drive carefully anyway, then got a snare down here. So if this happens, when this happens, whatever it is that's Dennis will then be recycled and will become part of a new ecosystem, which I think is great. You live forever. Your molecules, your elements will live forever, but not according to the plan that your parents left you. And let me tell you, it's going to happen to you. I ride my bike in the warmer months, and I go through the cemetery here. Beautiful place. The Oakwood Cemetery, it's a beautiful place to take a walk. And I'm friends with the grave digger there. It's sort of like out of Hamlet or something. And one day, he's just a really neat guy, very, very intelligent, very interested in, he's always digging up the drumlins and stuff there, and he's got lots of stories to tell me about the geology of Oakwood Cemetery. But one time he's digging it up, and we looked down, and I said, "What are you doing here? You're digging up an old grave." And he says, "Yeah, the family wants it buried somewhere else." And I looked down there, and I said, well, "That's a strange-looking casket. What is it?" And he says, "Oh, this guy died in 1943." And I'm thinking, 1943? I was born in 1943. All right, so we got something in common, sort of. and I look at the casket, and it was the best stainless steel casket, he said, my friend said, that you could have at the time, and it was all rusted out. And you could look right in there, and there's skull and long bones and stuff like that sitting there in the casket. So I'd say, so what? You preserve yourself as a mummy, and you could be preserved for thousands of years, but if they do it with formaldehyde, but that's horrible stuff, so, you got to face it. You're going to be recycled. Might as well just go gracefully quickly. Because this guy, as best as they could protect him, didn't matter. The microbes still got him. Okay, why are we talking about this? Okay. So, how do we connect this cosmic scale to the scale of Dennis or to any of the rest of you in this room? Well, I like this way. There was a great thinker in ecology called Rogan, and he kind of came up with this idea. And there's something called free energy. Free energy is high quality energy. It's energy available to do work. And free energy is photons coming out of the sun. They got a lot of punch. They can do work. Now, what happens is, over billions and billions of years, this hourglass passes the sands of time, from a state of high energy to a state of low energy. This is according to what, young lady in the blue?
Law of thermodynamics.
Excellent, right? Second law of thermodynamics. Very good. So, according to the second law of thermodynamics, energy is degraded from what we call free energy, that is the energy that's available to do work, to low temperature, I don't know, they don't have a word like free, but low temperature energy that is unavailable to do work. It isn't just that it's heat, it's that it's heat at very nearly the same temperature as the surrounding environment. Okay, now what has happened is that through evolution, starting 3.5 billion years ago, 4 billion years, some little paddle wheel, some little something got stuck in this hourglass. You can think about it this way. And what it's doing is it's grabbing a little of that free energy as it's going from high quality photons to low temperature gradient heat. So as those photons, some infinitesimally small fraction of the photons the sun sends out, of which is some infinitesimally small fraction of all the photons that are being blasted out from thermonuclear star reactions all through the universe, some little tiny fraction of that passes by the Earth, the only place we know this happens, and this little paddle wheel captures that energy. How does this work? Can I have a volunteer, please? Volunteer? Physically fit volunteer. Yes, sir. Come on up. Okay. Now, what we have, what is the process and what is the stuff by which this energy is captured? Just hang loose. What is it? Come on, come on, come on. Photosynthesis, right? And what is a very special molecule in which this takes place? Chlorophyll, of course. Okay, what's your name?
Adam.
Adam. Hi, Adam. Okay, Adam is the interior electron in the middle of the structure of a chlorophyll. In fact, let's see if we can get you just about here. Now, Adam, I want you to walk in a circle like this. Just walk. Yeah, just keep doing that, okay? Now, in the middle of a chlorophyll molecule, you have some very special arrangement of the elements of magnesium and nitrogen, I believe, that it's just like hemoglobin, incidentally, except the interior is just a little bit different. And they share some molecules like this between the different elements, share molecules. And the molecules are just kind of spinning around like this. They're at what's called a ground state. Gonna need another volunteer. And so, keep going. Hey, come on. And they're always spinning. Now, a photon comes into the sun and hits that electron. And what does the molecule do?
Goes into a larger orbit?
Yeah, it goes into a larger orbit. And what that molecule has done, make your orbit larger, has captured that photon, the energy in that photon, just like happened here with Adam. Now, what then happens to that energy? He's got more energy like a ballerina spinning with her arms out at a given rotation speed has more energy than when she spins at the same rate like this. That's why when the ballerina is spinning like this, or ice skater, and she puts her arms in like this, then all that energy is converted to faster rotation of less mass, and she speeds up. Now, what happens then is that all kinds of other molecules in the leaf, DPN, DPNH2, there's a whole bunch of stuff you learn about in biochemistry, come along, and what happens is that they're specially, come on, act like an excited molecule. Grab his, come along and grab that energy, and you go into a higher energy state. That's a higher energy state. Okay, he's in a higher energy state. You go back to your original, smaller rotation, okay? And this happens again. Now, each time you come by, you grab another bit of energy. Okay, here comes another photon. Watch out. Okay, now you hand it off. Okay, thank you very much. Okay, what happens is we've captured this high energy coming in from the only source, essentially only source important to life, which is the sun. And where's the other guy? What's your name?
Ryan.
Right, and so Ryan then goes and he passes some of that energy this way and some of this energy this way, and it runs all the machinery of life. So that's fundamentally how the world, the biological world, works. Now, in fact, if we got a carnivore behind you, what's your name?
Mike.
So Mike comes along and takes a bite out of the plant, or he's an herbivore, and then that energy is passed from you to Mike. What's your name?
Jennifer.
And if Jennifer is a carnivore who eats the herbivore, take a bite of his finger, please. Okay, then the energy is transferred along through the food chains. So life is all about the capture and the transfer of energy, both within an individual organism such as a green plant and through ecosystems. Some tiny fraction of which ends up right now keeping you warm. Feel that warmth right there? You're nice and warm. Ladies, this would be a nice guy to sleep with in the cold winter. So, this warmth, this came from the sun. What's your favorite breakfast cereal?
Wheaties.
Through Wheaties, captured by the wheat in the Wheaties, goes through the whole vast American agro-industrial enterprise, into your cereal bowl, and is now being dissipated into heat according to the second law of thermodynamics. We call this stuff here that intercepts the energy, and you see I have it passed along in gears like you saw up here this morning. We call this the machinery of life. And the machinery of life, it's a machine. It's a machine. A machine is an instrument that uses energy to do work. And what's the main work that life does? What is he doing? Who said maintenance? Somebody. Maintenance? Yeah, maintenance. Good. Speak up. You're right. Maintenance, metabolism. He's keeping his stuff together. And that's always requiring energy. So there's very little absolute homeostasis in nature. In fact, we used to think, for example, tropical forests were stable. Now we understand they're always changing. They're always turning over. Just like Dennis's cells in his skin are always turning over. His body is consuming cells all the time. Say, yeah, you're no good anymore. Get rid of it. Trees drop leaves. Even pine trees drop leaves. They say, you're no good anymore. And they get rid of it because what's happened is over time, things wear out. They wear down, they wear out, they get disease organisms chew on them, or all kinds of things happen to them. So periodically, it's easy for a deciduous tree in New York, they drop their leaves, but tropical trees that are evergreen all year round in these rainforests I was just in, they're dropping their leaves all the time too, just because it isn't worthwhile maintaining them anymore. Such as if you, like me, you know, I got a 15-year-old, 18-year-old car, but you know, at some point it isn't going to be worth maintaining it anymore. What happens then to this energy that the organisms capture? Let's take a look at what happens specifically in an animal. From here, you know, you can tell who likes to fish around here for trout, so here's a trout. And this is a sort of a summary of the energy budget of any animal, of a fish. And the first thing is, this is the energy available, or I would maybe say energy intake. Now, of course, there's a lot of energy not captured. A trout is what's called a drift feeder. It sits in one place in a stream and waggles his tail to maintain his position. If he sees a nice mayfly or an insect of some kind, or a little fish, or crayfish coming down, drifting with the current, and he'll go and grab it. The trout is investing energy into getting more energy. Why is he doing it? Now, it's like this guy up here. I says, you know, how come you're so interested in girls? And he says, well, because it feels good. I say, no, that's not the right answer. It's because it felt good to your ancestors. Why does the trout eat? Because he knows, or she knows, he needs energy to maintain his cellular integrity, to fight entropy, to do all the things of life. No, because he's hungry. So the hunger sensation that makes you go out and try and do all kinds of things, like have a horrible job or whatever to get money to eat, that is built into you because those of your ancestors who did not have a hunger center may not have eaten enough and may not have had the energy reserves when tough times came. Something like that. You can understand how that would go, I think. So the trout basically is hungry. Now the trout, of course, as any trout fisherman know. How many trout fishermen here? Not so many. As every trout fisherman knows, the trout balances his hunger against his caution, right? So he doesn't just eat everything that comes down. He'll look at it pretty carefully and say, that looks good and that looks dangerous. They know that incredibly, especially when they've been fished for a little bit. It makes them very interesting to fish for. So the energy comes in, and where does that energy go? Well, about 20 or 30% of it simply goes right through the fish. Actually, maybe I should have drawn it coming out here, as feces. So that's the energy that is not assimilated. Make sure you know the word assimilated. Assimilated means the energy is passed across your gut. Now, what is this energy like? Fundamentally, it's sugars. It's biological molecules, small biological molecules. They're moved across the gut, moved around in the blood of the fish, or you, stored in the liver, stored in fat tissues, and then it can be mobilized if needed at some other time. Now, of the energy that's assimilated, some is lost as nitrogenous waste. When you or a fish takes a leak, you're losing some energy. Ammonia, for example, is what makes pee smell so intense, especially if you don't flush the toilet for a few days. Do it just for experiments. And that's ammonia. Ammonia is a high energy compound. But your body's got to get rid of this nitrogen some way, and that's the way, we could talk about it a lot in some later course, but that's basically how we get rid of our nitrogenous waste, and especially in our diet where we eat much more nitrogen than we have any use for, and so we get rid of this nitrogenous waste. The majority of the energy that's used by the fish is just used for maintenance metabolism, for keeping the cellular integrity together. For example, think about the lining of your gut. What's the problem with if you're a gut cell? Let's pretend you're a gut cell. What's your problem? What's your big problem? You're sitting in a soup that's trying to digest you. There's digestive enzymes all around. So always the lining of your gut is being digested. And so what happens is that as the lining of your gut is being digested, you've got to keep rebuilding those important cells that are able to do the assimilation that you absolutely need to keep yourself together and to maintain this wonderful DNA structure that your parents left you, and also for the energy to work and do all the other things of life, okay? So that's just an example of how the energy is used for respiration. Now there's another use of energy. It's for active metabolism. So if the trout is hungry and he sees some yummy insect over there, he will invest energy in a burst of speed and go and grab that insect. For example, he might live under a rock. He doesn't like not being under the rock because the kingfisher or the osprey might grab him. So he makes an energy-intensive dash out, grabs the insect, and brings it back. And in fact, there have been some wonderful studies that were done by some people at SUNY and at, what's that nice little college just north of Albany? Siena College. Beautiful work that they did about fish in a stream will only go and eat when the expected energy gain is greater than the expected energy loss of predation. What's the loss of predation? Well, 100%. The fish knows that in its genes because it's been selected for to know when it makes sense to go and grab that mayfly and when it makes sense, because the predation is too high, to stay under the rock. They only do it on the average, of course, because sometimes they get caught by the osprey. What? Well, will not contribute to future genetics of trout, will he? He gets caught by the osprey. Okay, now.